And if they have, either they are disjoint or they are equal to each other, just like cosets in a group. If you take any two cosets, then either they are disjoint or they are equal to each other. So in a similar way, HAB is equal to H, HB is equal to H, HA is equal to H. So it means that HAB is equal to HB also, and HAB is equal to HA also. This we have. So HAB, basically we have AB, HA and AB, HB, both we have. So we can apply the previous lemma, that is by lemma 2.2.4, correct? Lambda B and lambda rho B and lambda A are bijections from H onto H itself, correct? This will be by lemma 2.4. That is rho B by H, it will be what? 1 1 onto map, and lambda A by H is 1 1 onto map from H to H, isn't it? Because if you see previous lemma, so there is a map from lambda x by H, lambda rho y by hx is a bijection from hx onto hx itself. Now here hx is what? H class, so it is replaced by H, correct? And also if you talk about hy, then it is again H class, so it is replaced by H. So basically we have this thing, H to H, H to H, both are bijections, correct? So which implies what? It implies what? It implies that HB, because if you take any element from here, so H rho B will be what? H rho B. H rho B is what? Right translation basically. So basically from here what we can say? See, remember what is Green's lemma? Green's lemma is what? Rho S by LA, isn't it? And when you apply X rho S, it is what? XS. Yeah, if you write rho LA or HA, doesn't matter. So X rho S is what? XS, correct? So XS, so here rho B, it means that it implies that HB belongs to H for every H belongs to H. So it implies that AH belongs to H for every H belongs to H. So now we again apply lemma 2.4. How? See, this is what? HB belongs to H. H is here, H is also equal to H. Basically, rho H. Whenever X, Y, H, X, we can apply lemma 2.2.4, correct? So X, Y, H, X here, X, Y, H, X and X, Y, H, Y when we have, then we can apply lemma 2.2.4, and H is also equal to here HB. Okay, so it is equal to what? H, we can write like this, isn't it? And we can write like this here, H. So HB, H, what does it implies? Now apply whenever X, Y, H, X. So X, Y, H, X. If we have this, then we get rho Y by Hx. Rho Y by Hx. It means that basically we can write like since B is also you write like this here, HB, and you write H as HA. So it is HB like this, correct. Now apply X, Y, HX, X, Y, HX. If you remember this, X, Y, HY like this, okay. And here AH, A. So it is X, Y, X. So X, Y, H, X, correct. So now it will be what? When X, Y, H, X, now you apply by lemma 2.2.4, it will be what? Rho Y, isn't it? So rho H by H, H to H, it will be what? 1 onto map, correct. And if XY, then again lambda x means lambda h from H, so it from H to H, it is again 1 onto map, is it? So rho h by h is a 1 onto map from H to H, and lambda h by h is a 1 onto map from H to H, correct. These things we have. So from here what we can say also that it implies that you take any element here, so basically it will be what? H this is right translation, remember, this is left translation. So when rho s by HA, X rho s is what? XS. So it will give H is equal to H, and it gives H is equal to H, correct, because it is 1 onto map. So we have H, and it is for every H belongs to H. For every H belongs to H, that is for every H belongs to H, we have this thing basically. So it implies that finally H square is equal to H. When it is for every H belongs to H, it means H square is equal to H, and H square equal to H. This is the definition of subgroup. If you see in the beginning, this is the definition of subgroup. So it directly implies that H is a subgroup of S. When H square is equal to H, and H is a subset of semigroup S, and H square is equal to H, then H is a subgroup of S. So in this way we have proved the Green's theorem, correct. So basically what is the trick to prove this? We have to apply 2 times lemma 2.2.4, isn't it? And for this we have to always keep in the mind the Green's lemma. How we apply that? Whenever rho s by HA, then X rho s is what? XS. S will be on the right side because rho s is the right translation, lambda is the left translation. So all these things we have to keep in mind, and we have to apply 2 times the previous lemma 2.2.24, then we will able to prove Green's theorem, correct. So finally we finish this lecture with the upcoming corollary of this result. See, what is corollary? Corollary means the consequence of this theorem. So corollary. Corollary 2.2.6. If E is an idempotent in a semigroup S, then He is a subgroup of S. And full stop. And no H class can contain more than one idempotent. Can contain more than one idempotent. Proof. So basically you see E belongs to He, correct? And also E is equal to E square, that belongs to He square. Isn't it? So He intersection He square is non-empty. So if H is an H class in the semigroups, then if H square intersection H is non-empty, then what we have by Green's theorem? H square is equal to H. So we apply Green's theorem. So by Green's theorem, He square is equal to He, correct? This we have by Green's theorem, and when He square is equal to He, so He is what? He square is equal to He, and He is what? Subgroup of S, isn't it? And as He is a group, no group contain more than one idempotent. Idempotent element in a group is the only identity element of the group, isn't it? So this part is proved that no H class can contain more than one idempotent. We have proved this, isn't it? If E is idempotent in a semigroup, then He is a subgroup of S, correct? This we have proved, and no H class can contain more than one idempotent because He being group cannot contain more than one idempotent. So in this way we have proved that no H class can contain more than one idempotent. So in this way we have proved Green's theorem and its corollary. So I will continue posting lectures. Don't worry about the syllabus. Keep on working and do all assignments, assignment 1, assignment 2, and submit at my email. Okay, thanks a lot.